Good morning, everyone. Hope you are all doing great. Today, we will go to the next lecture, which is gonna be about studying or the optimality analysis when we have an equal constraint. Okay, let's go through this. We are at the equality constraint case, and this is gonna be involved in our midterm, inshallah. This is really very simple. It's not compared to the complexity of the stuff that we went to go through. This is gonna be really very short and testable. So we need to discuss this in this lecture, the case of constrained optimization of functions in two main variables and with one equality constraint. This is an introduction to what's going to happen down the road. So the first step, we will study three methods that we will go through. The first of them, it's gonna be the graphical method, and then the implicit function method and the substitution method. These are the three methods that we will handle, inshallah. But before we start, we need to understand what's an optimization problem subject to a quality constraint looks like. And this is why we will try to go one of the very famous problems in economics that we will go through. Let us study one of the, as I told you, well-known problems in the economy, which is the consumer problem. This is one. This problem is famous, and every one of us is subject to this case in some part of his life or daily choices. So, if you want to go abroad, or if you want to travel, if you need a new computer, if you need to buy a new car, yeah, I need to buy a new car or a new house or to buy a wedding ring or something, you will come to this economical model, which in economics, the consumer problem refers to how a rational consumer chooses the best combination of goods, services to maximize their utility, their satisfaction, given their budget constraint, plus what they want to really do or what they really need to have. They have limitation on their budgets, as all of us do. So let's say that the objective function is u of x and y, and it is the objective function that the consumer wishing to maximize of his or her utility function. And it is subject to one of the quality constraint, as we explained previously. Now, facing this limited strict budget constraint, we should choose the best solution that exists. Okay, so the problem of maximizing or minimizing a function subject to quality constraint can be formed in this manner. This is the objective function required to be optimal, subject to this visible region, which is gonna be satisfied by the constraint. يبقى انا عايز اختار احسن حل بس تحت القيود اللي انا بشوفها دي. Remarks: we would like to find the best solution from the set of visible solutions that exist. First of all, satisfy the equality set of constraints. We should remark that the number of decision of variables must be greater than the equality constraints that we have in order to have some freedom in the choice of our solution. The first and the most easiest method, the graphical methods, as we will see shortly in the coming slides. It's really very simple and easy to do. In case of an optimization problem with two decision variables and one equality constraint, this is going to be handleable and accessible for us. So the first step that we will do is to identify the visible region that will constrain us with all solutions that satisfy simultaneously all equality constraints. Let's represent the set of all solutions that will satisfy the constraints of the problem. Number two, identify the level curves of the objective function. We will need to identify the level curves of the objective function. Number then also in this point, I will need to generalize the expression of the level curve that should be identified. Identify the optimal solution from finally by the help of the level curves of the problem and the visible area of solution. To clarify all of this, I will take just only a simple example as we will see. Here, consider the following problem and find its optimal solution if it exists. I want to maximize or to get the optimal solution of x plus y, but it is subject to the circle, which is x squared plus y squared equal to 4. So I need to get one of the points of the circumference of this circle, but with maximizing values of x plus y, which is the objective function. Here we go once more. We want to determine the point of the circumference of a circle centered at the origin and with radius equal to 2 that optimize the function given. So the first step, I will need to identify the visible area of solution. And that's really very simple. All I have to do is to graph the this circle. So I will go to my sketching and start graphing this circle with a radius of 2. Now, after identifying the visible area of solution, which inside the circle, I will go to my level curve, which is x plus y. And in order to be able to graph it, I will consider it x plus y equal to some value of k. This value will lead to y as a function, and x can be both this expression in y equal to negative of x plus k. If k equal to 0, I will have the line y minus x, as you can see, so with the slope of negative 1. This value or this function can be the largest point and the minimum point. So it can use it, we can use it to get the maximum point or the minimum point on the circumference. So here's our line at k equals 0, k equal 1. I will start to increase these lines if I want to have it graphically till it tangent be a tangent in this direction, which is y equal x perpendicular in this direction. I will increase it in the direction of y equal x till getting the point of maximality, or in the other direction to get the point of minimality. Remarking that the optimal solution will belong to the line perpendicular to y minus x. This is y minus x, the case that we are dealing about. So the direction of increase will be perpendicular to it. This is the increasing for the value of the function, and that's for the decreasing of this value of function, till it intersects the visible area of solution. So if I want to do this, all I have to do is to consider y equal x and make a substitution in the visible area of solution, which is going to come up to 2x squared equal 4, which means x will be maximum at x equal root 2 and the minimum at x equal to negative 2. Now I succeeded in having the optimal points, the maximum and the minimum points using graphical solution, which is really a very standard and very simple way to analyze this. And also the value of the function at the critical point, it simply can be evaluated just making the substitution in the value of the function at root 2 and root 2, combining these two conditions together, or at negative 2 and the negative 2, and you will get your result either for a maximization value and for a minimization value. So I have the extremum point and the extremum value of the function at that point. Now we will go the implicit function, which is also a really very simple way in order to analyze this case. In the implicit substitution method, it's really very easy to do. All I have to do is to get my objective function implicitly as one of the variables function in the other, or to get the implicit derivative and get the implicit derivative of the condition, which is g, and at the optimality point, both of them will equal to each other. We depend on this fact. So if I have the objective function or the function required to be optimized, and I have the constraint in the equality, at the optimal solution, the level curve of the objective function is tangent to the constraint. Both of them will be tangent to each other. So if both the objective function and the constraint are differentiable functions, then the extremum points, the slope of the function implicitly defined by the level curve of the objective is equal to the slope. So all I have to do is to get them implicitly. So first, I will get the derivative of the function implicitly defined by the level curve of the objective function. So I will get my objective function, put it equal to 0, getting this function which equal to 0, and start differentiating with respect to x, and then differentiating with respect to y, and getting one of them with respect to the other. So getting dy by dx, and that's one of the reasons why we took the implicit function theory. So it's a minus partial f partial x partial f partial y. So now I have the partial derivative implicitly for the objective function. Doing the same with the constraint, derivative of function implicitly divided by the constraint, also will put it equal to 0, getting this function once more, making the derivative of this new function, and putting them equal together. That's the key in order to get the condition of optimality. So once more, getting the implicit function derivative, getting the constraint implicit derivative, putting them equal together, and they should be equal to the optimality point that we are seeing. Here we go. That's the main point that I told you about. Back to our example, we have x plus y and x squared plus y squared equal to 4. We will exactly do the same steps that we saw previously. So simply, all I have to do is to get the implicit function for the optimal one and getting the implicit derivative for the constraint, then equating them both together according to this relation. So simply, all I have to do is to consider x plus y equal to 0. Derivative with respect to x is going to be 1. Derivative with respect to y is going to be 1. And this is 1 over 1, which is the implicit derivative with respect to y. I'm sorry, y to x. Same way like the implicit derivative, which with respect to x and y. So it's going to be 2x divided by a 2 over y, which means that's going to be 2x over 2y. Then I will take this relation and make the substitution in the constraint by letting x equal to y, I will end up having the same optimality point, and I can get the optimal solution relative to these 2 points exactly the same. Y will be root 2 and negative root 2, and substituting in the optimal function, I will get the results. Now to the last problem, which is or method, which is the substitution method. This is really, the idea is really very simple. All I have to do is to substitute by the constraint in the main function that I have, or the main function that we need to discuss its optimality. And this is really very simple. I will take the constraint function, reduce it, and then substitute in the main function, and the problem will be reduced to just constraint optimization problem involving two problems into one variable unconstrained problem. So we will change it from having one constrained problem into unconstrained problem. So the idea is to substitute by the constraint into the objective function of one variable as a function in the other variable, which will reduce the problem to be one variable unconstrained problem, like exactly the one what we solved. So back to our problem. This is x and y. The constraint is x squared plus y squared equal to 4. Try to get y as a function in x, which is really very simple. Moving x squared to the other side, taking square root. So it will be either positive root of 4 minus x squared or negative of 4 minus x squared, which is going to lead us for y greater than or equal to 0 case or y less than 0 case. I will go for the optimality of when the root is positive, x plus root of 4 minus x squared. The analysis here is really very simple. Get the first derivative, put it equal to 0, get the critical points, substitute in the objective function, and then finally you will have your test. Is it a maxima or minima or whatever? Same way goes for the second problem. So if we try to do this simply, this is f1. I will get f dash and put it equal to 0. And once we do so, we will have the condition for optimality, just squaring both sides to avoid the square root. It's going to come up to 4 equal to x squared. That's x equal to positive or negative root 2. Since we are in the positive side, I will consider just only the positive value, which is root 2. So this is the one that will be considered. I will go for the second derivative. It's really very simple, but you don't have to shave it or so. And then start substituting by root 2, which is going to come up to a negative value, which means it's a maximization for the value of the function when x is root 2, y is equal to root 2, and the value will be as you can see. Similar analysis will be done when for the other curve or for the other branch, which is x minus the square root of 4 minus x squared, exactly in a similar manner, getting the first derivative, putting it equal to 0 to get critical points, which is going to happen also by root 2 or negative root 2. Since we are in the negative side, I will use negative root 2. Making the substitution in the main function, I will get the value of y. And getting the second order derivative and resubstituting, so we will have a value greater than 0, which implies that we will have a minimal point or a minimum point at this point. Exactly the same analysis. And by the end of this method, which is really very simple, as you can see, now we come to this challenge. Please try to solve this problem. It's really very simple. You have your f function and subject to the x square, y square, z square equal to 9. Try to think how to go through this function in similar manner. Maximize the given function subject to the constraint of a sphere with a radius of 3, exactly as we saw. Thank you very much for listening. And I'm sorry for these videos. We can go through them once more in the university with more clarification, if you like. It's my pleasure to be with you, and thank you very much. Hope you enjoyed this short video. I appreciate it so much, and I wish you the best as always. Thank you. And please, if you have any question, do not hesitate to send it to me through WhatsApp or in the university or in the office hours, whatever you want to do. Thank you. Appreciate it. I'm really, very happy that I could end this video at the time being. Thank you very much. Thank you. Bye bye. Thank you.